I'd like to record the demo, but I think I have to get all your parents' permission first. Because you guys would be on camera, so I can't do that, I guess. So again, temperature, concentration, those two, how do they affect reaction rate? Give it more energy, more collisions, faster reactions. Add more particles, more collisions, because there's just straight up more particles to run into. Increase the effect of collisions, increase reaction rate. All right, what's the last one? Surface area. We talked about catalyst last week. That's another one too, but we already talked about it. Surface area, last one. Go quick here. So surface area, the book calls it particle size. Why particle size?
Because.
Let's take Jake for example. Jake, what does your family do? Chop down trees. Okay, so imagine we have a real big tree. So one
like a
tree.
Redwood, a redwood. California redwood.
All right, that's kind of sad, but chop down a giant tree, and then we want to make paper out of it. What has to happen to that tree first?
You gotta cut it up.
Cut it up into small pieces, pulp, right? Okay, so when I say particle size, it means the same thing as surface area. Jake, tell me how. When I say particle size, it's the same thing as surface area. Explain. Based on the tree analogy. So you have one big tree, but you want to make paper, so you got to cut it into small, tiny pieces or pulp.
I don't make paper.
I know he doesn't.
Wait, you're not the guy with the mustache and stuff that delivers the paper to school? Oh man.
What do you think, Jake?
You say that one more time.
Yep. How is surface area, and particle size the same thing?
Because the size of the particle is its surface area.
So a big tree or the pulp that big tree turns into, what has more surface area? It's not the same.
No. So I got it.
Think about it.
I got
if
it.
I want to touch the middle of the tree, what do I have to do? Right. But if it's a big pile of sawdust, it's probably easier that.
Oh, so the pile of sawdust has more surface area?
Right, and the particles are bigger or smaller than the tree.
They're small.
Smaller, right. So we take something big and grind it into a small powder or small pieces, more of it's exposed. That's why the book calls it particle size. So if we increase surface area, which means smaller pieces, right? Smaller pieces. Sorry, smaller pieces, looks like 5. Smaller pieces, that's going to increase reaction rate. Increase reaction rate. Going too fast for myself here. So increase surface area, increase reaction rate. Why is that? More particles are exposed. And what does that increase? It increases the number of effective collisions. Increases the number. So again, it's all about those collisions, but how do you get there? Increase the temp, that's one way. Give it more energy. Add more particles. That's concentration. That's another way. And then here's another one. Increase surface area. So again, more collisions. And then a catalyst does the same as well, but that's not something we're taking notes on. We already did. Okay, so hurry up and get that down. Next, equilibrium. I'm going to write it up there, give you some examples, define it, and then I need 9 of you to come up here. So think about who wants to volunteer.
Can I pick who goes up?
No, I'll pick if we don't have volunteers. Good to go?
Yeah.
Okay. All right, here we go. And you had your review packet due Friday. I'm going to go probably right to the bell, so I'm just making sure we're clear. Review packet Friday, no homework due tomorrow. Okay. Equilibrium, here we go. Equilibrium. I'm going to give you 2 examples. Put physical on the left side of the page, put chemical on the right side. So physical and chemical. I'll give you 2 examples before I give you the definition, so you have something to understand. So equilibrium can take place in a physical process or a chemical process. A physical process would be something like melting and freezing. So if you take H2O solid, I want you to draw weird little arrows that look like that, and then H2O liquid, that's called equilibrium. And of course, this would be at 0 degrees Celsius. So if you have, a sample of water at 0, at zero, exactly zero, you have freezing and melting at the exact same time. That's called equilibrium. Going from solid to liquid would be our forward process. Liquid to solid would be our reverse. What equilibrium is when there's a process, physical or chemical, where two are happening at the same time. Two processes are occurring at the same time. We say forward and reverse. Think of a rotating door like a hotel. One of those revolving doors. You got people going in, people going out, and just imagine that there's always going to be the same amount of people going in and out at the exact same time. It's not a perfect analogy, but that's kind of what's happening. So every time one of these melts, one of these freezes. So they do it at the exact same time, simultaneously. That's called equilibrium. That's what this arrow represents, forward and reverse at the same time. Chemical would be a reaction, like nitrogen gas plus hydrogen gas. Give me that reversible arrow, that's what it's called, produces ammonia, NH3 gas. That's chemical because you're showing a chemical reaction here. You'd have to balance it. We need 3 H2s and 2 NH3s. So that's our chemical equilibrium. What does this mean? These two reactants, these two elements combine to make a product, a compound. At the exact same time, the product breaks down into the two reactants. What's that direction called, the forward? What type of reaction is that? Synthesis, good. What about the other one? Decomposition. So they're both occurring at the same time. So every time 4 of these, right, 3 plus 1, 4, makes 2 of those, the exact same time, 2 of these are breaking down into 4 of those. So it's simultaneous. That's what equilibrium is all about. You have forward and a reverse at the exact same time. So keep that in mind when I write the definition. All right? I know I'm going quick. Stay with me. Okay, so what is equilibrium? Let's define it. Any process / reaction where the forward reaction and reverse reaction. So anytime the forward and reverse reaction occur at the same rate. Any process or reaction where the forward reaction and reverse reaction occur at the same rate. And I say any because that's physical or chemical. So anytime you're forward, that means going to the right, and then reverse, going to the left, occur at the exact same rate. What does rate really mean? Speed. How fast it works, right? So in other words, they're working at the same speed. That's what that means. Now coming off of here, you got to make something very clear. The amount, this is the most important part of this equilibrium stuff right here. Next thing I'm going to write. The amount, or maybe amounts, I think I used the S earlier, of reactants and products always stay constant and balanced. That's underline constant and balanced. Those are the two most important words there. The amounts of reactants and products always stay constant and balanced. The word equilibrium sounds like the word equal is in there, but the word equal does not belong anywhere in our conversation. Constant and balanced is different than equal. And I'm going to show you right now how constant and balanced don't mean equal. I'm making a point to point this out because I don't necessarily think I do a good enough job every year teaching that, because kids still want to say equal. And I'm bringing it up because you'll get there on your own even if I don't. So I really want to stress constant and balanced. So I need 9 people. Anybody want to volunteer? I had to pick all of them for period 2. All right, we'll do it now. Isla, thanks for volunteering. Steph, thanks for volunteering. Ryan, thanks for volunteering. Blake, thanks for volunteering. Jake, thanks for volunteering. How many is that? Come on up.
That's 5.
5. Nicole, thanks for volunteering. Zach, thanks for volunteering. You can stop that, Jake. You're not supposed to be on the camera. Stop it.
Yeah, Jake, there's supposed to be a camera. Oh my